Welcome to Theory of Computation. This is lecture number 28. We are discussing the proof of the Cook-Levin theorem. As you know, the Cook-Levin theorem says that one problem called satisfiability is NP-complete. What that means is that every problem in NP can be reduced in polynomial time to satisfiability. I have been emphasizing the fact that Cook-Levin theorem is nothing but a statement that says that we can translate every problem which is in NP into a satisfiability problem. So all it is saying is that the language of satisfiability or the problem of satisfiability is powerful enough to capture the whole class NP. I consider the proof of Cook-Levin theorem to be one of the most beautiful proofs in computer science. It is an important theorem and it is a deep theorem. However, I find that the proof is extremely intuitive. There are no unexpected tricks involved in the proof. All it is just unraveling of definitions and then looking at what is the power of satisfiability and going about it in a very sensible way. The Cook-Levin theorem is also deep, not only because its proof requires several ideas, but because of the deep consequences that it has. What it says is that if one is trying to find a polynomial time algorithm for problems in NP, then we can just concentrate on this one question called satisfiability. On the other hand, if we are trying to prove that P is not equal to NP, then satisfiability is the prime candidate. We should be trying to prove that there is no polynomial time algorithm for satisfiability. What I would want you to do is to be very clear that all we are saying is that any problem in NP can be transformed, can be changed, can be reduced to satisfiability in polynomial time. We are not saying any statement about how difficult it is to solve satisfiability or how difficult it is to solve a given problem in NP. We are not talking about how many resources are required to solve satisfiability. We're not saying anything about how many resources are required to solve a given problem in NP. All this theorem is saying is that it is very easy to translate every problem in NP into a satisfiability question. So, in some sense, it's measuring the relative complexity of two problems. Take any arbitrary question in NP, take any arbitrary language in NP, and take the language of satisfiability. What it's saying is that you can translate this language into a question in satisfiability. So it's talking about the relative difficulty of two problems, not the absolute difficulty. So it is not saying that satisfiability can be solved in polynomial time or anything like that. Neither it is saying that any arbitrary language can be solved in polynomial time or anything like that. All it is saying is that one can translate that language into this one language, satisfiability. What does that do for us? Well, it identifies a very, very important and interesting problem in the class NP. It identifies a complete problem. We call satisfiability NP complete because in some sense it has all the complexity of the class NP. And right now I'm not talking about the definition, the mathematical definition of the word NP complete. Mathematically, NP completeness has a very precise definition. However, we could have chosen some other word to express this notion. The reason the word complete is being used here is because this definition shows us, and Cook-Levin theorem shows us, that the problem of satisfiability is so important that if we were to solve it in polynomial time, then the whole class P will equal to NP. On the other hand, if we were able to show that satisfiability is not in NP, then we would show that P is not equal to NP. In fact, anyone who proves that P is not equal to NP would, as a consequence, be able to prove that satisfiability does not have a polynomial time algorithm. Once again, it's very important to understand that we're talking about relative difficulty of solving problems. We're saying that every problem in NP is in some sense easier than the satisfiability question. However, take this statement and think about it. Here you're looking at things from the point of view of polynomial time solvability. If you look at things from a different point of view, they will have different complexities. But if the only concern that we have is polynomial time solvability of problems in NP, well, then all problems in this sense are easier or less difficult than the problem of satisfiability. And therefore, we call satisfiability NP complete. Now, let's think about how we started with the proof of Cook-Levin theorem. Well, to prove Cook-Levin theorem, what we had was an arbitrary language L, and the only thing we knew about this language was that it belongs to the class NP. What we had to do was somehow show that this language is reducible to satisfiability. Before that, in the lecture previous to the last lecture, we had seen how to reduce three-colorability to satisfiability. So we had seen one little instance of Cook-Levin theorem. And we saw that satisfiability or propositional logic is a very powerful language. You could express the fact that a graph is three-colorable. What you could do is you could take a graph, and by looking at the graph, you could quickly come up with a formula such that this formula would be satisfiable if and only if the original graph was three-colorable. In some sense, this formula was saying that there exists a way to assign colors to vertices such that three colors to the vertices of this graph such that no edge would be monochromatic. So we translated the problem of three-colorability to satisfiability. And in order to do that, we had to develop various tricks. One of the tricks or techniques that we developed was being able to say that each vertex is assigned a unique color. So each vertex is assigned at least one color, and no vertex is assigned more than one color. And we were able to come up with a Boolean formula, which you looked at, and we looked at closely. So this was one way of expressing, saying each vertex is assigned a separate color, or unique color. Well, we use the same technique in the Cook-Levin theorem. But in the Cook-Levin theorem, we don't know much about the problem. The only thing we know is that the problem is in the class NP. So all we know is that there is a non-deterministic Turing machine that accepts this language in polynomial time. So now what we will do is we will take that non-deterministic Turing machine M, which accepts the language L, and suppose you give me one instance X of this problem. What I would do is, by looking at this instance X, create a formula phi sub X such that phi sub X would be satisfiable if and only if M accepts X. Well, now let's think about what it means for a non-deterministic Turing machine M to accept X. Well, a Turing machine accepts X if and only if at least one computation branch of it accepts X. Well, suppose now that you have a Turing machine M and there is an input X. And what you want to do is you want to convince me that this non-deterministic Turing machine M will accept its a given input X. And let's say that I ask you to prove this fact to me. How would you go about it? Well, we said that we can find a very nice proof of this thing. I can ask you to give me a proof in form of a tableau. I would want you to write down a large table, and this table will have certain properties. First of all, this table will not be very large because the non-deterministic Turing machine runs in polynomial time, so it will have only polynomial number of rows and polynomial number of columns. So it will have n to the k rows and n to the k columns for some k. Now the way you will fill out this table is The first row of this table will be the initial configuration of this Turing machine M on the input X. And you'll fill out the rows, and for me to check whether this proof is correct, all I will have to do is to check certain properties in this table. And what are those properties? Well, the first property is that I'll make sure that you put exactly one entry in each cell of this table. So, in some sense, I'll make sure that you have filled out the table properly. You have not put two things in one table, or you have not left any entries blank or unfilled in this table. So that would be the first thing I would check. The second thing I would check is that the first row of this table corresponds to the initial configuration of the Turing machine M on the input X. And that would be another property I would want in this table. So that's property number 2. The third property I would want in this table is that since you are claiming that M accepts X, I would want one configuration in this table in which the accept state appears. So one of the configurations in this table should be an accepting configuration. So that's the third property I would want in this table. And the last and the most important property I would want in this table was that this table, every row of this table corresponds to a configuration. So what I would want to check is that every configuration yields the next configuration according to the rules of the transition table of this Turing machine. What I would want to know is that the computation history that you have given me, the series of configurations that you have given me, which you claim to say corresponds to an accepting branch of M on input X, you have not actually cheated. You have only followed the transition that are allowed by this Turing machine. Once I perform all these checks on this tabloid, I would be convinced that the Turing machine M would accept X. Now, since the language of M is L, I would also be convinced that X is an element of the language L. Well, so what we will do is we'll say that if X is an L, then M accepts X, which means that there exists such a tabloid. Now, instead of expressing that M accepts X, we will simply express the fact that there exists a tabloid which shows that M accepts X. And what we want to do is we want to now do it in the language of satisfiability. So that was the outline of the Cook-Levin theorem. Once we can express the fact that this tabloid exists in the language of satisfiability, so we'll make a formula phi sub X, which will say there exists a tabloid in which the first row corresponds to the initial configuration of M on X, and it has all the other properties. Then this phi sub X would be satisfiable if and only if the tabloid exists, if and only if X is in L. And if we can compute phi sub X in polynomial time, then that would give us our reducibility. So let's look at the Cook-Levin theorem and let's see how we were doing all the different components of the Cook-Levin theorem. And there was one last component that was missing, last piece of the puzzle. Let's see how we will fill that and complete our proof today. So last time we discussed the proof of Cook-Levin theorem, and here is the basic outline of the proof. We want to show that if L is an NP, then L is polynomial time reducible to SAT. The idea is that if L is an NP, then L is accepted by a non-deterministic Turing machine M in polynomial time. So the hypothesis that L is an NP immediately leads us to this Turing machine M, which is a non-deterministic Turing machine and accepts the language X. What we know about this Turing machine is it's non-deterministic, it accepts the language L, and it runs in polynomial time. So these are the three things we get to assume to start our proof. Let's go further. What we want to do, we want to show that there is a function f that we can compute in polynomial time such that x is in L if and only if f of x is in satisfiability. Well, this is the very definition of reducibility. So what I'm telling you right now is nothing more than what we are to do, what is required in the conclusion of the proof. We are asked to produce a reducibility or show that a reducibility exists. That's what we want to do. We will do this by creating a formula phi sub x such that phi sub x is satisfiable if and only if m accepts x. This would be the same as creating a formula phi sub x which is satisfiable if and only if x is in L. And the reason for that is we have this Turing machine, non-deterministic Turing machine M, that accepts L. So saying x is in L is equivalent to saying that M accepts x. Now how will we go about this? What we want to do is come up with this function f. We will do this by creating this formula phi sub x such that phi sub x is satisfiable if and only if M accepts x. What we know is that M accepts x, then we can make a tabloid that shows an accepting computation of M on x. This tabloid will be n to the k by n to the k tabloid, and that is a simple consequence of the fact that M runs in polynomial time. We know that M runs in polynomial time, so we can assume that it runs in time n to the k. This means that the number of configurations needed to lead to an accepting configuration would not be more than n to the k. Therefore, this tabloid will have only n to the k rows. Similarly, we know that a Turing machine can only write on the first n to the k cells if it's taking time n to the k. So we do not need to know the contents of the tape after n to the k cells. So this whole tabloid will be summarized n to the k by n to the k array. The formula phi sub x is going to be satisfiable if and only if such a tabloid exists. So now what we have done is gone from the language to from the question or from the requirement that x is in L, we've converted that and said it's equivalent to saying that M accepts x, and now we're saying that is equivalent to saying that there exists a tabloid with certain properties. Now, another idea was to use several variables. Remember that our eventual goal is to output a formula which is in propositional logic. So it will be a formula over Boolean variables, and it'll have ands and ors and nots and things like that. So we will create this formula, and of course to create formula we need Boolean variables. So we will take several Boolean variables. So the variable x sub I j s would be true if and only if in the ijth cell of the tabloid we put the symbol s. So let's look at the interpretation of each variable in this formula that we are going to create. We will have several variables, and the variable xijs will be true if and only if we place the symbol s in the ijth cell of the tabloid. So now we are leading towards our goal, that is satisfiability. We have some Boolean variables. Let's continue with this. This tabloid has to have several properties. Let's look at these properties one by one and see what are the properties that this tabloid needs to have. Each entry of this tabloid has exactly one symbol in it. So that's the first requirement, that when I look at this tabloid, each cell of the tabloid has exactly one symbol written in it, and these symbols will be either symbols from tape alphabets or states or the hash sign. But in one cell of the tabloid, we will have exactly one symbol, not more than that, not less than that. That's a requirement. You're not allowed to put more than one symbol in any cell. You're not allowed to leave out any cell without a symbol. So that's one requirement of this tabloid, requirement number one. The second one is that the first configuration, the first row of this tabloid correspond to the initial configuration of M on X. So if I read out the first row, then it should be hash followed by the first symbol of the input, followed by the second symbol of the input, all the way up to n symbols of the input, and then followed by blanks. So the first row of this tableau is dictated. And that's another requirement. Since I'm saying that a given input is accepted by this Turing machine, the first row must correspond to the initial configuration of this machine on the input that is given to this machine. There is another requirement that I want this tableau to fulfill. This tableau corresponds to an accepting computation. What does that mean? That somewhere in this tableau I must see the accept state. That's another requirement, because the claim is that M accepts X, and this tableau gives us that proof. So I must see M accepting its input. The last and the most important requirement that we will discuss today is the following. Each configuration row is obtained from the previous row through the yields relation of the Turing machine. So every configuration, every row in this tableau is a configuration. The next configuration must follow from the yields relation that comes from the transition function of this Turing machine. That means all I'm saying is that you have not cheated while making this tableau. And this is extremely important requirement, and the tableau must fulfill this. So these are the 4 requirements that we have on this tableau. Now, we want to express all these properties in propositional logic. First, we say that exactly each entry of the tableau has one symbol in it. Well, we did this last time, and we came up with a formula called phi sub cell. Phi sub cell was saying that every cell has exactly one symbol in it. And of course, we used a trick that we learned from our 3-color problem to be able to say that each cell has exactly one symbol in it. That was one component that we developed in the last lecture. That formula we call phi sub cell. This formula phi sub cell expressed the fact that each table entry had exactly one symbol. Here, what does it mean, express the fact? Well, remember we have Boolean variables, and each Boolean variables x, I, j, s corresponds to putting s in the ith, jth cell. Now, what I can do is I can set x11 a to be true, which means in the cell number 11 I have put a. But I can also set x11b to be true, which means that in the cell 11 I also have a b. Well, if I do that, then my assignment corresponds to putting 2 elements in the cell 11. If I do that, that assignment will make phi sub cell false, because this assignment does not fulfill the requirement. On the other hand, if I assign the Boolean variables in such a way that they correspond to putting exactly one symbol in each cell, then phi sub cell will be true. So this is what we made last time. We call this Boolean formula phi sub cell. Then the second requirement was that the first computation is the initial computation of M on the input X. And for this, we use the formula phi sub start to express this. We made a formula which was only talking about the first row of this tableau, and it was saying that the first symbol in the first row must be a hash sign. The second symbol in the first row must be the initial state. The third symbol in the first row must be the first character of the input. The fourth symbol in the first row must be the second character of the input, and so on. And then finally it was saying that all the other symbols in the first row must be blanks. And so it was an and of a bunch of things, and it was simply saying that the first row should correspond to the initial configuration of the machine on the given input. Notice that phi sub start is the only formula component that we have made so far which depends on the input. The formula phi sub cell doesn't really depend on the input. All I need to know is how long the input is, how big the tabloid, and I can create phi sub cell. Phi sub start, I need to know what the input is. The third component was that the tabloid corresponds to an accepting computation. We use the formula phi sub accept to express this. How did we do that? Phi sub accept, we also did it in the last lecture. It was just an OR of several variables, and it was just saying that somewhere in the tabloid I must see an accept state. What we were trying to do last time was to do the last component. What is the last component? We must come up with a formula which expresses the fact that each configuration row is obtained from the previous row through the yields relation. We will use a very elaborate formula for this. If we can do that, then we'll take the AND of all these formulas, and that will be our phi sub x, and that would show us that the reducibility exists. Let's see how we will do this. In the last lecture, we looked very closely at phi sub cell, phi sub start, and phi sub accept. In this lecture, we want to concentrate on the formula phi sub move. So remember, phi sub move will express the fact that every row follows from the other row through the transition function or through the yields relation of this non-deterministic Turing machine. Next, we started with the concept of legal windows. We said a 2x3 window is legal if it can appear in a possible computation of the Turing machine M. So, if I give you a tabloid and I take a window of size 2x3 and ask you to focus on it, by looking at that window and by looking at the transition function of the Turing machine, you can tell me whether this can ever happen or not. Well, the concept of legal window, or the formal definition of the legal window, is just saying that if you have the top 3 characters, then is it possible for the Turing machine to yield the next 3 characters? Let's look at a few legal windows in order to clarify this concept, and then in your handout you'll be given an exact definition of this thing, but intuitively this notion is not very difficult to understand. Let us take a machine with the following transitions. Suppose the machine on the state Q0 reading A has to write a B, go into Q2 and move right. On the other hand, when the machine is in state Q0 and it's reading a B, it can either go to Q1, write a A and move right, or go to Q2, write a C and move left. So this is a non-deterministic Turing machine. So this is the transition function of this Turing machine. I've taken a very simple example. Now let's look at what possible legal windows can be there and why they are legal. Let's look at the first window. On the top we have a hash sign AB, and on the bottom we have a hash sign AB. So imagine that you have a Turing machine which has a hash sign A and a B written there, and the tape head is very far away. Now as the tape head moves here, it is not going to change this hash sign A and B. So in the next configuration, you will have a hash sign A and B intact as they were in the first configuration. So this is a window that can appear while the machine is doing a computation. So we call this a legal window. Let's look at the second window. It has BAB on the top and BAB on the bottom. Well, once again, this is a legal window because suppose you have BAB written somewhere on the tape and the head is nowhere near that position. Well, in that case, BAB will be copied down in the next configuration. So this would be a window that can appear while the machine is doing a computation. So once again, this is a legal window. Let's look at a third legal window. This is Q0 AB followed by B, Q2, B. Well, in this case, the machine is in the state Q0, it is reading a A and then that is followed by a B. Well, when the machine reads A in the state Q0, the transition function says that it has to go into the state Q2 and move to the right. So what will appear in the next configuration is the head would have moved to the right, and now the symbol which has become B will be written before the head position, and that B which the head was not reading will be copied down. So if the machine were in the state Q0 reading a A which had a B after that, and I look at that window, then the bottom part of that window will appear in the next configuration. So once again, this is a legal window. Let's look at the last legal window on your screen. It's Q0 BB followed by BCB. Well, you can ask, where did the state go? Well, remember that when the machine is in Q0 and it's reading a B, the machine is allowed to move left, so it'll move out of the window. And of course, the B has been replaced with a C. And since we are not observing anything on the left, we have no idea what was there. So if there was a possible B, that will appear in the window. So these are all legal windows that I can see while some computation of the Turing machine M is happening. So these are legal windows. In order to enforce this concept, let us look at some illegal windows which cannot happen. Here are some illegal windows. We have a hash sign AB followed by a hash sign A hash sign. Well, remember that hash sign was a special symbol. When we made the tableau, we put hashes on the left and the right side of it just to help us out to know how big the tape is. So a hash sign is not something that the Turing machine is allowed to write, and therefore a hash sign can never, a B can never turn into a hash sign, or this configuration can never happen, so it's illegal. The second illegal window is BAB followed by BCB. Well, a tape symbol cannot automatically change. The head has to be reading it for a tape symbol to change. And if we look at this window again, which is BAB and then BCB, it seems to say that A all of a sudden, without the head being anywhere near it, changed to a C, which is impossible. Therefore, this window is illegal. Let's look at the other two illegal windows and see why they are illegal. The next window is Q0A B followed by BQ1B. Well, if you look at the transition function of M, when the machine is in Q0 and it's reading A, the transition function only allows it to go into the state Q2. And here the machine has, here it seems like the machine has gone into Q1, which is not allowed by its transition function, and therefore this window is illegal. The last example is Q0BB, and on the bottom row we have CQ2B. Once again, look at the transition function as I have told you and think about a bit. The transition function does not allow this window ever to appear, and therefore all of these windows are illegal. Here are some very critical observations that I want to make. I want to make these observations. They are very critical in the proof and they are very important for you to understand. First observation is that by looking at the transition function of M, we can compute the set of all legal windows. The second observation is that computing all legal windows can be done once and for all. For that, I do not need to have any input of the machine M. So it does not need to be computed for any given input. Although this point is not that critical in the proof, but it's important that by looking at the machine only and no input of it, I can compute all its legal windows. The third point is that if we have a tableau that has the first configuration, which is the initial configuration, and each window is legal in the tableau, then the tableau corresponds to a computation of M on X. So these are the three very important observations. Let's discuss each one of them one by one. Let's start with the first one. The first one says that by observing the transition function of M, we can compute the set of all legal windows. Well, this is not very hard to see. In your homework, I've given you NTM and asked you to compute all possible legal windows. Let us nevertheless outline a simple but time-consuming method to do this. Note that these windows are of size 2 by 3. So these windows have size 2 by 3, and so therefore they have 6 possible entries. Each possible entry in this window is one of the symbols, or one tape symbol, or a state, or something like that. So there are only finitely many things that you can put in each cell of these windows. Now they have only 6 possible entries. So if each cell can have r entries, then there are total r to the 6 windows. So let's say each entry in the cell has r possible entries, then the total number of windows would be r to the 6, and this is only a finite number of them. Thus, what I can do is go through every possible windows and try to figure out if it is legal or not. So to compute the set of all possible legal windows, I can generate all possible windows and test if each one of them is legal. And if anyone that I find legal, I can output it. And that way I would have outputted the set of all legal windows. So my algorithm to output the set of all legal windows is simply the following. For each possible window W, if W is legal, then output W. This algorithm will compute all possible legal windows provided that we can test if a window is legal, and that is not very difficult to do. Well, what you would do is, if I give you a window and ask you if it's a legal window, you'll start first of all seeing if something unusual is happening in this window, if one of the symbols is all of a sudden changing without the head not being nearby. You would discard that window if that is happening. You would also see if the window has, any row of the window has more than 2 states in it, you will discard all those windows. You'll come up with these simple tests. Then if a window passes all these tests, you would see that if it respects the transition function. If it does, then you'll say the window is legal, otherwise it's not. So what I can do is I can compute the set of all possible legal windows. Note that this thing has to be done once for a given machine. It need not be computed when the input X is given to the machine. So the legal windows do not depend on the input to the machine, it only depends on the transition table of the machine. Thus, we can compute the set of all legal windows once and for all. The last point that I made was that if every window in a tableau is legal, then the tableau must correspond to a computation of M on an input X. So suppose if the first row of this window corresponds to the initial configuration of M on a given input X, and all the windows are legal, then the whole tableau corresponds to a computation branch of M on X. Why is that? Let's have a look at it. The reason is because of the definition of the legal window is designed to enforce this. That is because a 2x3 window will always ensure that the middle element in the next configuration comes from a legal move of the non-deterministic Turing machine M. Let's look at this figure, and this figure says that if you know 3 consecutive elements in a row of the tableau, then from there you should be able to figure out the middle element of the next row of the tableau. So these legal windows are designed to enforce that each middle element is coming from a legal move of the non-deterministic Turing machine. And then when I enforce the fact that all windows are legal, that gives me that shows me that almost the whole row is legal except for the last 2 hash signs. But I've also put those legal windows saying that hash signs never change and no new hash signs appear. So if the first row corresponds to a configuration, then the next row will correspond to a configuration which comes after one move of this non-deterministic Turing machine. Actually, to prove this, we need to do 2 small exercises. First of all, let C and D be 2 configurations such that C yields D. Now let us write down C and D as 2 rows in the tableau. What you have to prove is that all 2x3 windows created in this tableau are legal. Let us look at a figure in which we have a configuration C up there and followed by a configuration D, which is yielded by the configuration C. And as we can see, all the windows created in this tableau or this part of the tableau are all legal. The second exercise that we need to do is the following. Suppose now that we have two configurations C and D such that C does not yield D. So there is no way to go from the configuration C to the configuration D using legal moves of the Turing machine. Now suppose we write C and D as two rows in this tableau. What we can prove is that at least one of the 2x3 windows is going to be illegal. Well, why is that? Suppose you have a configuration C and then you write down another configuration D and C does not yield D. Well, that would mean in order to write down D, you will have to cheat somewhere. You will have to violate the transition function of the Turing machine M or do something which is not allowed. As soon as you try to do that, you will create an illegal window. Thus, if I insist that all the windows should be legal, then C must follow D. Once we have done these two exercises, we realize that if all windows of size 2x3 are legal in a tableau, then it must correspond to a valid computation of M on an given input X. Let us look at an example. In this case, you have a configuration C which does not yield a configuration D, and as it is shown to you, this particular window that is being bolded out is illegal. Obviously, we have tried to cheat somewhere and we have managed to create an illegal window. So now, with these observations and with these tools that we have developed, we are now in a position to create our promised formula, Boolean formula, which we call phi sub cell, which would say that all windows of size 6, all 2x3 windows in this tableau are legal. Let us go one step at a time and try to make this formula phi sub L. First, what we will do is we will compute the set of all legal windows L, which is equal to W1, W2 up to WT. We'll compute that using the algorithm. And now what we want to say, suppose I just want to say that the first window is legal. How would I express that? How would I say that fact, that the first window is legal? Well, I can say this by saying that the first window is either W1 or W2 or W3 and so on. So I will say that the first window in this tableau, the window whose left upper corner is 1, 1, is legal. I would say that either the first window is W1 or W2 or W3 or W4 all the way up to WT. Now remember, OR is an operation that is allowed in propositional logic. So OR is an operation that we can use when we pose a satisfiability question. So since OR is allowed, so all I have to do is to be able to say that the first window is equal to W1, and once I do that, and I have to be able to say that the first window is equal to W2 and all that. If I say that, then I can take the OR of them, and that will say that the first window is legal. Let's see now how this would be done. Let's once again do this by an example. Let's say that the first legal window that we have computed is the following. It is hash Q0 A followed by hash B Q2. So that is a legal window. What we want to say is the first window in our tableau is equal to this particular window. How would I say that? Well, I've said that for you on the screen. Let's see what I have written. What we can do is we can simply write x11 comma hash, which says that the first 1 entry of this tableau has a hash sign in it. 1 entry of the tableau has Q0 in it. Therefore, I have ANDed that with x12 Q0 and x13 comma A. So that's saying that the 13 entry has A in it. x21 comma hash. So the second row, first column has a hash in it. x22, which means the second row, second column has a B in it. And x23 comma Q2, which says that the second row, third column has a Q2 in it. So this Boolean expression is going to be true if and only if you put exactly these things in the first 2x3 window. Well, so this way I've been able to say that the first window is equal to this legal window? Well, how would I say that an arbitrary window is equal to this particular window? Well, instead of using 1, 1, if I want to talk about the ijth window, I'll just use ij indices instead of the index 1, 1. So if I want to say that the ijth window is equal to this particular window, then I will write xij comma hash and xij plus 1 comma q naught and xij plus 2 comma a and xi plus 1 comma j comma hash and xi plus 1 j plus 1 comma b and xi plus 1 comma j plus 2 comma q2. So here what I'm doing is actually saying this cell must be this and 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 this cell must be this. When I say that 6 times, I am actually saying that this particular window must be equal to the window W1. Now, let us denote mu sub ij be the formula that says that the ith jth window is equal to W sub L. So, I can make this formula mu I comma j L, which says that the ith jth window corresponds to the lth legal window. Now, what if I write down the following Boolean formula? Well, this formula is OR over L going from 1 to t mu I j L. Well, this formula just says that the ijth window is either W1 or W2 or W3 and so on, which is equivalent to saying that the ijth window is a legal window. So this is equivalent to saying that the ijth window is legal. So this formula that I have created will be true if and only if I assign the variables in such a way that in the ijth window in the tableau, I have put a legal window. Now, in satisfiability, I have the power of doing ANDs. So I will AND this over all entries. So let us look at this new formula. So this formula is an AND over all ij and the ORs of all L going from 1 to t mu I j L. And this formula says that all windows are legal. And this is our phi sub move. So, using the language of satisfiability, I have created a formula phi sub move which will be satisfied by assignments that correspond to putting symbols in this tableau in such a way such that every window is legal. Now what I will do is take the AND of these 4 components that I have made. So our grand Boolean formula that we have created, phi sub x, is going to be phi sub cell and phi sub start and phi sub accept and phi sub move. This formula phi sub x will have the property that it is satisfiable if and only if x is accepted by m, and therefore this formula is going to be creating this formula will be the reducibility that I am looking for. Let's summarize all this. This formula is satisfiable if and only if all 4 components of it are satisfiable. Phi sub cell is satisfiable if and only if we have an assignment of the variable that corresponds to putting one symbol in each entry of the tableau, exactly one symbol. Thus, the tableau is filled properly. Phi sub start is satisfied if and only if the variable assignment corresponds to filling each row or the first row with the initial configuration of m on x. Phi sub accept is satisfied if the variable assignment corresponds to having accept state somewhere in the tableau. This means the tableau encodes an accepting computation. Lastly and most importantly, phi sub move, the way we have created is satisfied if the assignment corresponds to filling rows in such a way that they follow legal moves of the machine. So in summary, what we can say is that phi sub x is going to be satisfied if and only if this tableau corresponds to an accepting computation of m on input x. So what have we finally done? All we have to do is to finish the proof of Cook-Levin theorem. We will simply consider this following algorithm. It takes an input x and it computes phi sub x and outputs it. This algorithm computes a function in polynomial time. Our discussion shows that this is a polynomial time reducibility from the language L to satisfiability. Thus, L is polynomial time reducible to SAT, and this completes the proof of the Cook-Levin theorem. So, what we have done is now formally completed the proof of Cook-Levin theorem. In the next lecture, we will discuss the Cook-Levin theorem briefly and then start proving many other problems which are NP complete. I'll see you next time. Thank you and goodbye.